Second part of thinking about evaluating nitrogen needs is going to focus on plant measurements. Okay, so again, our outline for this module is plant testing. We've already discussed soil testing, and we can broadly think about plant testing as using our eyeballs, visual symptoms. We can think about plant analysis, and then finally plant sensing. So that will be the outline. Okay, so an important distinction in plants is the mobility of nutrients in that plant. Okay, now again, this is not mobility of nutrient in soil, but plants themselves. And so we can dichotomize nutrients broadly into either mobile or immobile nutrients within the plant itself. That is, how much the ability of that nutrient to actually be translocated from one plant part to the next. Mobile nutrients include nitrogen, phosphorus, potassium. So the big three are mobile. They're able to be translocated. Also, things like magnesium, chloride, and molybdenum are all mobile nutrients. And what that means is as that plant is growing, it's able to essentially cannibalize itself and translocate nutrients if it's in deficiency from older tissues to newer tissues. So when we're thinking about visual symptoms for mobile nutrients, it's typically the older leaves that show deficiency first. Conversely, immobile nutrients are nutrients that typically are not do not get translocated within the plant at all, or to a lesser extent. And so these are nutrients like sulfur, calcium, boron, iron, manganese, zinc, and copper. Okay, so not surprisingly, these are, since they cannot get translocated, and if we run into a period of deficiency, it's these younger leaves that are typically affected. Here's just a nice kind of dichotomous key for diagnosing nutrient deficiencies visually. And again, that first split you can see is it young leaves or old leaves. N, P, and K are all old leaves. So you can spend some time kind of going through this if you like. And thinking about nitrogen deficiency in crops. Okay, so this is a lot of text, but it's just kind of nice to have as reference. We understand the important role that at this point that nitrogen plays in plants. Adequate N produces a dark green color in leaves from high levels of chlorophyll. As a mobile nutrient in plants, deficiency symptoms first appear in these older leaves like we're talking about, right? So it's light green, it's a lightening of leaves, turns yellow, then develops on younger plant parts, right? So symptoms include stunted, spindly, lack of vigor in terms of the plant itself, low protein content, fewer leaves, fewer seeds, fewer vegetative parts. Nitrogen deficiency will cause early maturity in annual crops and, of course, significantly reduce yield and the quality of that harvestable product. So nitrogen, in terms of how it's manifested, it's not this like perfectly, you can't classify it as like, oh, that's that one thing, that's like telltale nitrogen deficiency. Depending on the plant, depending on etc., because nitrogen plays a lot of different roles in plants, but we're thinking about a typical from a dark green to a yellowing and just a reduced plant in terms of the total biomass. And so here's a picture of corn leaves. The healthy leaves, of course, is a dark green, plenty of chlorophyll. And in nitrogen, for corn itself, we often see a firing along the midrib. Okay, so a yellowing, a general yellowing, and then often we can see this as firing or a chlorosis, what I'm calling firing. That's just a term meaning like a yellowing in a chlorotic region of that plant. Okay, so here's a picture of kind of classic nitrogen deficiency in corn, but it's not always this like perfect firing along the midrib of this vein. That's the main vein that splits that leaf into two parts. It often looks like this, and you can see this if you're driving any year, any given time in Ohio. if there's an edge of the field that's experienced a lot of nitrogen loss, or for whatever reason the applicator didn't fully apply that rate as it was going, on the edges or in swells or on kind of high points in a field, we can see plants that just do not look nearly as healthy or as vigorous as other plants. Soybeans, nitrogen deficiency is very rare in soybeans. If we have that, it's because we have a lack of N fixation, and that could be partly because of, say, very low soil pH levels. It could be because there hasn't been a history of a legume in this field for a long time, or because that seed has not been inoculated. Those are all, they can happen for sure, but I've yet to see truly well-diagnosed nitrogen deficiency in soybeans. Typically, we're buying seed that have inoculate, and people understand when I'm saying inoculate, that's actual, the rhizobia bacteria that are in a preserved state that provide a seed coating, and that is planted with the seed. That seed breaks dormancy, and then the bacteria are there to do their job in terms of forming nodules and fixing nitrogen. Deficiency in wheat, again, a general yellowing that happens, and then so deficiency symptoms are our first clue that the plant's not happy and something's wrong, right? But deficiency symptoms are never definitive. Like we're using these visual symptoms. Oh, the plant looks sick, or this plant looks, blah, 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 not happy. There's this spot in the field. These are things that are good kind of first clues, but they don't really ever. The jury's still out until we do something else, until we actually follow that up with some sort of analysis. And plant analysis is the next step, okay? When we use plant analysis, we're often looking at concentration of nutrients. And again, this is kind of this generalized relationship that we've talked about already. But there's some concentration that a plant needs. If it's below that concentration, or this critical nutrient range, or sometimes critical level, we have a deficiency. So this is concentration of a nutrient by the actual growth percentage of maximum. We're at 100. There's no decline in vigor and productivity. But if we start to drop below 100, then we do see, okay? At some point, we hit above that critical nutrient range. So additional fertilization or additional supply of that nutrient is not going to have any impact on plant growth. But the plant, depending on the nutrient, might consume it luxuriously, right? So it might increase in the concentration of the plant for a rainy day. And then at some point, there might be too much of a good thing, and we can develop toxicity symptoms. Okay, so again, this is that generalized relationship. And we can go out, and in the field, we can measure concentration of a plant part or a whole plant. But we need, and we can get a value, we can get a concentration of nitrogen or concentration of phosphorus in that tissue material, but we need that to be referenced to something. We need the background work to be that has been done to tell us, well, typically, soybeans should be in this range to that range, or apple leaves should be in this range to that range, and that's the kind of the crux to making this framework work and tissue analysis be useful. Analysis can happen in the field, okay? So there's things that are out there like sap test, meters, there's little indicator strips that are available that we can actually do measurements, specifically nitrogen testing in the field. And how these work is that, again, these little like throwaway indicator strips that might be color coded to measure nitrate. We could use, most common example is petiole nitrate, using kind of these handheld meters for this. Okay, so here's an example of a project that my lab's leading on hops, looking at hops in the north central region, primarily Ohio, Michigan, and Indiana, and then evaluating the ability of these little handheld nitrate meters. These are a few $100s, and you sample hop leaves. You take this petiole, this little piece out, which are typically a storage vessel and very nitrogen rich, and we crush these up with this garlic press that we saw in this last slide, and we measure, put that on the indicator diode, and then we measure concentration of nitrate in that petiole sap. So it's a petiole nitrate is what we typically call that. Here's a link for, if you're interested, some YouTube videos. Part of this project, this is a research project that we're looking at trying to develop better ranges of nitrate for hop growers, so hop growers can manage nitrogen better and have a better idea of what nitrogen needs that they should run through their irrigation lines. And so if you're interested in this or want to learn more from kind of a specialty crop perspective, you can certainly click on that, and there's several videos in there that will lead you through it. But of course, there's lots of things that we grow, not just corn, soybean, and wheat, or hops. There's lots of vegetables, and there's guides that are listed for what would be sufficient. And depending on the crop growth, here this is broccoli and collards. We can think about 6 leaf stages. We can think about prior to harvest or at harvest. What are those nitrate levels in fresh petiole sap, quote unquote, supposed to be for for a healthy plant? So these are kind of considered sufficiency levels. So we want a value, say pepper at first flower, to be somewhere between 14 and 1600. If it's lower than that, might indicate that we need more nitrogen, and there's a potential for nitrogen deficiency. Above that, again, potential that we're over fertilizing, don't need that. So nitrate in sap, also potassium as an indicator. So there's nitrate meters. There's also these little handheld potassium meters as well. So doing things in the field have a lot of value. We can think about advantages for that. They're typically, you've got to invest in like a meter or some strips, but typically they'll pay for themselves over time if you use them. You can make biggest advantage is that you can make same day. You can go out there, collect the information that you need, and then make a management decision right there on the spot. The disadvantage is that your measurements might not be that accurate, right? We're talking about a simple meter, and with simplicity, might come error or noticeable variation. If we take and sample plant parts and send that to the lab for the analysis, we're going to assume that lab-based measurements are typically going to be more precise and accurate. There's better quality control in professional commercial laboratories than in the back of a pickup truck, for example, or on a tailgate. And labs have mechanisms for long-term data storage, and so you could go back, if you're not particularly good at keeping records, you can go back and ask labs for, what were the values last year, the last 3 years, or last 10 years, and they're going to have that information associated with your account. Disadvantages is that labs, can be expensive. For a typical analysis, it might be $15 to $25 for kind of a plant analysis, and you've got to wait several days. Labs are very good at turning results around really quick, but it's still never going to be same day. It's going to be 2, 3, 4 days down the line. So I'll just run really quickly about some common field-based measurements that we would run in the lab. And so the first one is ear leaf sampling in corn. So we call this R1 corn for when corn is silking. This is a point in time, and for all of our field crops, it's often a point in time when the crop has gone through a burst of growth. So corn, of course, will grow rapidly, places a large demand of nutrients of the soil when it's pulling soil up and growing in that rapid growth phase before it starts tasseling. And that's the best time that you're actually going to see a nutrient deficiency. So we target these period rapid growth. So R1 happens in corn, and we call this ear leaf. We go out, we find that ear of corn, and it's that primary ear, maybe not that secondary ear, but the primary ear. We go and we essentially just rip that ear right off, that leaf right off that ear leaf. And we do that for maybe 10 or 15, maybe 20 actual plants. If we see a problem area in the field, we're going to do that for the problem area, and then we're going to do independently a second sample that's in a good area and compare those values. But we could go out and just sample a field generically and submit those samples, those leaves, for analysis, and then we'll get a total nutrient content of what the nutrient concentrations, N, P, K, et cetera, are in that leaf. Okay. For soybeans, we do this at the upper trifoliate, and so we go out and we pick. This is typically right at R1 or R2 flowering, so that can happen quite quickly. But we go out and we find one of the most recently developed trifoliate leaflets, right? Like this 3 set of leaves. We pick that off. We take this nutrient-rich petiole and discard that, and we submit this for analysis to the lab. We're never just going to sample one tiny thing. We're going to sample multiple plants and try to get some kind of representative sampling. For wheat, we would do the same thing, but we would do flag leaf. Typically, this would be considered late, but the flag leaf on small grains is that last leaf before it sends that head up, that reproductive structure, right, that spikelet up for grain development. So we're going to sample these and submit those. And for something like alfalfa or a hay crop, we might sample the first 6 inches at early bloom, or perhaps right before bloom, and we go out and we clip approximately 6 inches off multiple plants. This little picture says 35 plants, so a lot of these, throw them in a bag, either drop them off at a laboratory or throw them in the mail. That would, preferably they get there the next day for lab analysis. Okay. And there's tables that are out there. There's tables that are published. This is a terribly pixelated table from the Tri-State recommendations. We'll talk about this in a second, but it gives you a range. Here's corn ear leaf sampled at silking. That's R1 essentially, and then here are the nutrient ranges for the different macro and micronutrients. And there are guides, for not say petiole testing, but actual plant tissue, and that's what we have here for different vegetable crops: carrots, radishes, romaine, bok choy, etc. And so this is like an important component of management. And we can think of this in terms of the information that we get. We can look at our values relative to these quote-unquote book values and try to see where we're at. But we can also use tissue testing as a way to assess our management from year to year and where our concentrations going up, are they decreasing, et cetera, okay? So we send it off to a lab and we magically get a number back. We get a data sheet, sample submission with a lot of these things. And what does that actually mean? Or how does that actually happen? Well, very typically in commercial testing labs, they run use an ICP, or this inductively coupled plasma mass spectrometer, okay? And what they're going to do is you're going to take your plant sample, they're going to dry it overnight in an oven, they're going to grind that sample, and they're going to put this in a heating block with nitric acid typically. It's most common. They could even kind of cook it to ash it, but typically nitric acid digestion, it typically takes 2 to 4 hours depending on the method. That essentially liquefies that material. So they heat it and they put it in a strong acid, and it basically liquefies that material. It turns that solid plant material into kind of a liquid solution. They take that and they basically, this is an auto sampler. This isn't the best picture to see, but there's peristaltic pumps and tubing. They'll line these trays up. An auto sampler will come, and it will pump that solution into this ICP. And the ICP is an incredibly complex technical instrument that essentially what it does, it takes that solution, it turns it to a mist, and then it runs it through this argon plasma torch at an incredible temperature. That's what this picture is depicting. It takes all those proteins in plants, all those biochemical structures and enzymes, and it takes it. It decomposes all of that it sends it through this beam of energy, this plasma torch, and it atomizes and then ionizes everything. So it's broken down to its most fundamental component, and then it quantifies that. Okay, so if you want to get if you want to learn more about it, check out the first 4 minutes of this YouTube video. It's not to say that you're going to understand all the things, but it just gives you an appreciation of the complexity for this. And so commercial testing labs have these ICPs, and the big ones have them, 5, 6, 7 of these, and they're constantly running. So it's the workhorse for most commercial testing labs, and they're very quick. You can run many samples in an hour on these machines, and that's the point. Okay, so that's why commercial labs really implement these machines, because they can run lots and lots of samples on these guys over the course of a day. Cornstalk nitrate test is just another test I'll mention. This is an end of the season diagnostic test that answers the question, how effective was N management? And it's really kind of a plus or minus. Was it sufficient? Was it excessive? Was it insufficient? The way this works, it's kind of random in terms of the standardization for this, but you basically at reproductive maturity, that's not particularly when corn is ready to be harvested, but when it hits that R6 black layer, if that means anything to you. But it's when that plant is fully mature and that grain is cut off from the cob and it's ready to go. We measure 6 inches up, we make a cut, and we take an 8-inch segment. Okay, so that's the kind of standardized protocol and we'll go around and do this on, say, 15, 20 plants, and depending on where you're at in the field, et cetera, et cetera. We take that sample and we run, take that sample, dry it, grind it, extract nitrate with KCl, and then we run that. We quantify the nitrate-nitrogen concentration. Okay, and again, here's that nitrate concentration versus relative yield, and we can see there's a lot of scatter in the data, but typically when nitrate concentrations are low, we can see a dramatic drop in there. And so there's been a lot of work done at Purdue to kind of, other places as well, Iowa State, but Purdue most recently in terms of kind of calibrating this. And it's a pretty big range, and you can see from these data here, it's almost like a plus minus. Either it's not enough or it's plenty, right? Or it's some not too much in between. So low category is 250 ppm. Optimal is somewhere between 250 to 2,000 part per million, and then excessive would be over 2,000. So again, this is like a post-mortem after the end of the season to go back and look at your nitrogen program in corn specifically and see how you did. So this is a common test that, I don't know, it's not that farmers are running this every year, but it's certainly a tool that's out there if people want to use it. It's good to be aware of. Okay, so finally I'm going to talk about this idea of plant sensing. Okay, so this is kind of what I would define. The difference between analysis and sensing is that analysis is a destructive measurement and plant sensing is non-destructive. So one of the things that are out there are chlorophyll meters, and these essentially measure leaf greenness. They do a pretty good job. The idea is that as leaf greenness increases, the chlorophyll content increases. And it's just a little clip-on meter. it doesn't harm the leaf at all. You just kind of apply that, and then it's got this calibrated range of quote unquote the chlorophyll content, i.e. how green that leaf might be. And there's been work that's done, in Ohio and relatively recently, but showing that this is a pretty good tool. The question is are we actually going to go out to fields and measure this? And at that point, for that particular crop, is it going to be too late? Is it just kind of like a post after the fact indicator of how we're doing, or is it going to be something that we can make a nitrogen decision based on that? Okay. Other technologies exist. So the leaf chlorophyll measuring leaf greenness. This is a technology that has a lot of potential. It's been around for a while, but is used to a large extent, and it's a little tricky, but it's a great concept, and it's this NDVI. So it's this normalized difference vegetation index, and Trimble makes these handheld meters. Green Seeker is kind of the brand name that was developed out of Oklahoma State. Trimble has incorporated that technology into these meters, and they sell these for like $400 or $500, maybe $300. I'm not entirely sure, but the idea is that you would walk over corn rows when they're maybe knee or waist high. You get readings, and the reading is going to go from somewhere from 0 to 1. And that is going to be an indicator of how green the plant is. So it's this ratio of near infrared wavelength minus the visible wavelength divided by the near plus. And so if it's closer to 1, it's basically, it's got a high NDVI, and if it's closer to 0, it's a low NDVI. So the higher the number, the quote-unquote better that crop is. Now the rub with these is that varieties, this is typically used with corn, but you can see it can be used with any kind of crop, really. But we think of it in an Ohio context with corn, I guess. We have done some work, although there's still a lot of work to be done in terms of looking at this. But you can, not just do this by hand. You can do this with drones. You can do this with flyovers. There's a lot of ways that this is implemented. I'll say that there's units out there where they actually have individual sensors that are mounted on, these booms. So you can essentially get an on-the-fly nitrogen recommendation. Here we've got essentially a modified sprayer with, say, UAN as a nitrogen source in liquid form. This applicator is going to go. These are what are called Y drops. So there's essentially the tanks right here and fertilizer. There's pumps that are individually controlling, individual pumps that are controlling each one of these Y drops. And that Y drop is just simply a tube that's dribbling liquid nitrogen on that soil surface. Okay, so you could come in to corn at different stages, even when it's waist high or higher, and each one of these rows is going to get essentially a unique reading. That reading is on the fly going to get fed into a computer, and it's going to control how much nitrogen is administered through these Y drops. So, this is certainly what we would call precision ag technology, but all of this is going to depend on your formula, your algorithm for what NDVI reading should I have for that application rate. So there's a lot of work that is involved in developing that piece, right? And so one of the challenges with green seekers is that hybrids, varieties differ, and so we actually need a nitrogen reference strip, an enriched strip, where we're going to apply a whole bunch of nitrogen and make darn well sure that it's not limiting, right? And so once we do that, we say that's our ceiling. That's when the plant is as nitrogen rich as it possibly can be, and then everything should be subtracted from that. But for whatever reason, you wouldn't think that was such a big deal, but there's a lot of farmers that they just don't want to do that. They want to go and apply the same amount throughout the entire field, but it's a bit of a bit of a hurdle to get over to really kind of implement some of this stuff. Okay, so remote sensing. Again, we don't need to do this sensing on the ground, say on a boom or by hand, for example. We can do this via drone or by satellite or by flyover in aircraft. And of course, in ag, this is a huge push, this idea of digital or precision ag, right? And we're going to have say a lot more about this later in the semester, but I'll just leave it, as this. So, using visible remote sensing, this can be done with drones, airplanes, satellites, and in some ways there's a trade-off between cost versus resolution. Drones can fly really close to the field and get you really high resolution pics, but you're not going to be able to do that many acres. It's going to be more expensive if you're contracting someone to do that, collect that information for you. Airplane is pretty much how this is primarily done because it's very economical to collect lots of acres, images of acres, but also satellite imagery. Some satellite imagery is collected and publicly available, so you don't have to pay for it. But the resolution is going to be a lot smaller, meaning that they might be at a 10-meter resolution. Every 10 meters is a pixel, as opposed to to something that might be like every half a meter or every, say, 0.2 meters or something like that. So a lot of different variation of what is actually used. Some are specific bands, some is like hyperspectral band collection. So depending on what is emitted versus what is reflected back, these green seekers are what we call a active sensor, where there's actually a light source that's emitting and then bouncing back off the canopy. Okay, so that's an active sensor. When we're getting into this remote sensing concept, that's what we call passive sensing. So we're not sending any energy, any either near or infrared or visible light at this crop. It's just collecting what's bouncing off of that canopy from the sun. And so when it's cloudy versus when it's really sunny versus when it's rainy, like all these things will influence the quality of the picture and the spectra that you get. So it can be quite challenging, but there's a lot of work and there's a lot of interest in this, a lot of development, a lot of money being made, a lot of acres that are getting flown to collect things like visible light, infrared, multispectral bands, even thermal images, measuring the heat that's coming off that canopy as a measure of crop stress or as a measure of nutrient availability, water stress, pest pressure, et cetera, et cetera. So this is a really exciting field that's developing, but it's very, very complicated, and we need to understand it's potentially a piece of the puzzle in terms of managing, but it's not the Holy Grail. Wanted to point you to some sources for Ohio specifically. Field crops for corn, there's this maximum return of nitrogen. I'm going to talk about this in the next talk. For vegetable crops, there's a Midwest production guide, and for fruit crops, there's a home fruit guide production. You might think that every crop and every thing that we grow has this really well calibrated, designed recommendation for nitrogen. This is exactly what you should apply, this many pounds, Again, because of the dynamic nature of this, there's a lot of generalities. You go and pool, these vegetable crop or fruit crop guides, and you actually dig in there. And I'll post these on Carmen, but if you dig in there to look at like what the fertility recommendations are, they're actually quite vague and they're challenging. And then you say, oh, well, what about like I'm trying to establish a Christmas tree stand, or I'm trying to establish just a hardwood forest with planting some oaks or walnuts or whatever. It's like, how much N do I need? Well, yeah, I'd love to be able to tell you that if I had a great idea. A lot of times there hasn't been great calibration work that's done. That's like the majority of the time. Like actual nitrogen rate trials with something like, walnut trees, for example, or whatever it might be. And so a lot of times it's just kind of best guess or rule of thumb, or going out and dealing with people that work in that industry. What do you do? Tell me about your program. How do you actually fertilize? Do you do it much? Do you do it when those crops are in, or those trees or whatever are in the first year or second year, et cetera, et cetera. So just a word of caution that there's a lot of uncertainty that goes with nitrogen recommendations. Okay, so we've done a lot of work with some of these, major crops in Ohio, things like corn that are nitrogen loving, occupy lots and lots of acres. Vegetable crops play a very important role. Fruit crops play an important role in the Ohio economy and the ag sector. But there's a lot more diversity in terms of the plant type and how they're managed, and some of that work just simply hasn't been done. The source for plant tissue analysis values is this textbook, Plant Analysis. It's in its 3rd edition right now. It's like a ridiculous $300 book or something. I don't know. Maybe you can get a cheaper version. But if you want to know how much nitrogen should be in some, this crop or that crop, this is really the source that you go to. And these authors have, really kind of done a lot of legwork compiling this information to try to find these quote-unquote sufficiency levels. That is, what concentration of all these nutrients should be in any given crop. And then, of course, that's going to depend quite a bit on the plant part, the stage of development, et cetera, et cetera. So this is a textbook just to be aware of. So, all right, I'll end on that. And that's really kind of evaluating all the many ways that we might evaluate nitrogen needs in plants.